Welcome to the lesson for the DN5 assignment, graphically determining the normal force. Imagine a box sitting on an angled surface. The force of gravity will be pushing down on the box. If this surface was slick, we would expect the box to be sliding down the table. But like we said, the box is not moving. So that means there's a static force of friction that is resisting that movement. Gravity wants to push the box through the table, but the box does not go through the table because the table pushes up on the box. We call that the normal force. The force of gravity is pushing down. In our diagram, the static force of friction is pushing up and to the right, and the normal force is pushing up and to the left. When added together, these three vectors cancel each other out, and that is why the box is not moving. Again, the force of gravity is pushing down on the box, and we could write it as a push or a pull. So if the force of gravity is pulling down on the box, in these questions, we are going to break this force up into a perpendicular force of gravity and a parallel force of gravity. The parallel force of gravity is equal to the static force of friction if that box is not moving. And the perpendicular force of gravity is equal and opposite to the normal force. The box is not moving because all these forces cancel each other out. And this is how we're going to determine graphically the value of the normal force, by taking Fg, breaking it up into a Fg perpendicular and Fg parallel, and once we know the Fg perpendicular, that will equal the magnitude of Fn. If the box is sitting on a table, the force exerted on the table depends on three factors. Number one, the mass of the object. The heavier the object, the harder it pushes against the surface, thus the harder the surface has to push back. Two, the force pushing down on the box, typically the force of gravity. The higher we are in the atmosphere, the smaller the force of gravity. The smaller the force of gravity, the less the object pushes on the surface. This means the surface does not have to push up as hard. And the third is the angle the surface is relative to the force of gravity. The angle, which may not be initially intuitive, makes sense if you think of a box sitting on a flat table. The force being exerted by the box is completely pushing down on the table. But if the table is slowly tipped, the box begins to exert less force on the table. As the table is rotated from 0 degrees to 90 degrees, the force the box exerts on the surface, which was 100%, has now decreased to 0%. Now for the examples. We need to calculate the normal force for a 612-gram object sitting on a flat surface. For all our examples, it will be a 612-gram object. So the force of gravity will be the same in all the examples that we are doing today. So I have to figure out what the force of gravity is equal to on a 612-gram object. And we know the force of gravity equals mass times gravity. The mass has to be converted to kilograms, so 612 grams equals 0.612 kilograms, and acceleration due to gravity is 9.80 meters per second squared. We put that in our calculator, we get 5.9976 newtons. Correct that to three significant figures, that's 6.00 newtons. We're going to be drawing diagrams to scale, so we need to have a scale written into our notebook. And we are going to make 1 Newton equal to 1 centimeter. So for example A, a flat surface, we will draw a flat surface. then we will draw the box that is sitting on the table. We're going to put a dot so that we can draw all our forces either pushing or pulling on that same location. I want to draw the force of gravity. It's going to be pulling down on this box with a force of 6.00 newtons. So I'm going to take my ruler. I'm going to measure down 6 centimeters and draw FG. Now, if FG is pushing down, the table is pushing back up. And since the box isn't moving, it is pushing up with a force that is equal but opposite to what the force of gravity is in this situation. So I'm going to take my ruler, measure up 6 centimeters, and I'm going to draw the normal force. And the normal force is equal to 6.00 newtons. This time we have an angled surface. So I'm going to draw a dashed line, and I'm going to take my protractor and measure up 15 degrees from the horizontal, and then I will draw my surface. Somewhere on that surface, I will draw a box, and I'm going to place a dot where I'm going to draw all my vectors from. I will start with drawing gravity pulling the box down. So I'll take my ruler, measure 6 centimeters, and draw FG. Now I'll take my protractor, and I'm going to draw FG perpendicular. It has to be perpendicular to the surface. So I line up my protractor and draw a line that goes 90 degrees perpendicular to the surface. That will eventually be my FG perpendicular. Now I will draw my FG parallel. I'm going to place the protractor at the bottom of FG. I'm going to make my dashed line and measure up 30 degrees, and I'm going to draw a line that will run parallel to the surface. Now I have FG perpendicular and FG parallel drawn. Now I will get my eraser out. I will erase the excess line that I've drawn. I will know I've done this right to this point if I have a right angle between FG parallel and FG perpendicular. So like I said, I'll erase the line and put an arrowhead on FG parallel. I will erase the excess and put an arrowhead on FG perpendicular. Now I'll get my ruler out and measure the length of FG perpendicular. And it's somewhere between 5.7 and 5.8, but a lot closer to 5.7 than 5.8. So I'm going to take my ruler, I'm going to draw it at just over 5.7 centimeters long. And I'm going to write down my value of Fn, which is about 5.72 newtons, according to my diagram. Now let's calculate the normal force graphically if the surface is 55 degrees from the horizontal. So again, I will draw a dashed line. I will take out my protractor and measure up 55 degrees from the horizontal so I can draw my surface. I'll then draw a box on the surface, and I'll place a dot where I'm going to draw all of the vectors from. So I'll take my ruler. FG is equal to 6 newtons, so I will draw a line that is 6 centimeters long. Next, I'll draw FG perpendicular, so I will take my protractor, line it up so that 0 is on the surface, and then I will draw a dashed line that runs perpendicular to that surface. So at 90 degrees, I will draw a line much longer than required. Now to draw FG parallel, I will take my protractor and I will put it at the bottom of FG. I'm going to draw a dashed line and measure up 55 degrees. Now I will draw a line that runs parallel to the surface. If I've done everything correctly, I should have a right angle between FG parallel and FG perpendicular. Now I will erase the excess and put an arrowhead on FG parallel. I will erase the excess and put an arrowhead on FG perpendicular. And to figure out how long Fn is, I will measure the length of FG perpendicular. And that comes out to be about 3.5 centimeters. Looks like it's right on 0.5, so 3.5 centimeters. So I will move my ruler up Measure 3.5 centimeters and draw Fn, and then signify that Fn is equal to 3.5 newtons. Now for our last example. We're going to calculate the normal force for the same box, but it's sitting on a vertical surface. So we will start by drawing a vertical surface. We'll put a box on that surface. We'll put a dot where the forces will be drawn from, and the force of gravity will be pulling down with 6.0 newtons of force. And since the box is not being supported by the table in any way at all, it's just going to fall straight down, and the normal force is equal to 0 because the table is not pushing against the box at all, or the box is not leaning on the table in any way whatsoever. Things to keep in mind as you work through this assignment: these have to be drawn very carefully. When marked, I will place a transparency over the diagram to make sure it is accurate. Also, make sure that all forces have arrowheads to identify the direction of the vector. And that brings us to the end of this lesson. You're good to start working on that DN5 assignment.